Right now, in the dark, quiet space just behind your eyes, a signal is moving. It began somewhere in your ear, where the sound of this voice is landing on tiny structures thinner than a human hair, and it is traveling this very moment along a thread of nerve toward the part of your brain that turns sound into meaning. That signal is not sound anymore. It stopped being sound almost instantly. It became something else, something faster and stranger, something that moves through you the way a whisper moves through a hallway, quietly, urgently, right under the surface of your awareness. It is a tiny electrical pulse, and it is happening in you, constantly, without your permission or attention, thousands of times a second, for every sound you hear and every thought you have, and every breath you decide, almost never consciously, to take. You have been living inside electricity since before you had a name for it. It was there when you were a few weeks old in the womb, your heart already beating on its own private electrical rhythm, a small storm of charge sweeping through heart muscle in a wave, contracting it, releasing it, contracting it again, long before you had lungs full of air or eyes that had opened. It is there now, in this room, in the wires behind the walls, in the small device that may be playing this voice to you, in the quiet hum of anything plugged in nearby. And it is there in you, in the conversation happening right now between your ears and your brain, in the muscles slowly loosening in your shoulders, in the nerves in your feet that are, this moment, telling your brain something small and unremarkable, like the exact pressure of a blanket or the temperature of the air. And yet, despite all of this, despite living inside it, made partly out of it, surrounded by machines that run on it, most people never got a slow, patient explanation of what electricity actually is. Somewhere along the way, in a classroom or a textbook or a rushed conversation with an adult who was also a little unsure, we were handed some pieces, electrons, circuits. Don't stick a fork in the outlet. Lightning is electricity. Batteries have a plus and a minus end. And then the pieces were left scattered, unconnected, like puzzle pieces from different boxes. And most of us quietly agreed to stop asking questions about it and just use it instead. We flip switches. We charge phones. We complain when the power goes out. We do all of this while carrying around a hazy, half-formed idea of what is actually happening, an idea assembled from fragments, useful enough to get through a day but never quite settled, never quite whole. Tonight is not for assembling fragments. Tonight is for slowness. We are going to take electricity apart, the way you might take apart an old clock on a quiet afternoon, not to fix it, not because anything is wrong with it, but simply to see, piece by piece, laid out gently on a soft cloth, how it was built in the first place. We will start from nothing. We will start from before there were wires, before there were batteries, before anyone had a name for any of this, back when the strangest evidence of electricity in the world was a piece of fossilized tree resin, warmed by friction, mysteriously able to pull a feather toward itself through empty air. We will move slowly from there. There is no need to rush. There is nowhere else this needs to go tonight. I want you to notice, if you can, without straining, without trying too hard, that you do not need to remember anything I say. This is not a lesson with a test at the end. There is no quiz waiting for you in the morning about the difference between current and voltage. No flashcards, no pressure to retain a single fact. If your mind drifts, if a sentence slips past you and dissolves before it fully lands, that is completely fine. That is, in fact, sort of the point. You are welcome to let entire ideas float by unfinished, the way you'd let a boat pass by on a river while you sat on the bank, not needing to follow it to its destination, just watching it go. Here is the shape of what is coming. loosely, the way you might glance at a map before a long, unhurried walk, rather than memorizing every turn. We will begin with atoms, the almost unimaginably small building blocks that make up everything around you, including you, and we will look closely at one particular part of the atom, a nearly weightless, endlessly restless particle called the electron, because nearly everything about electricity, when you trace it back far enough, comes down to what electrons are doing, and more specifically, what they are doing when they move. From there, we will talk about static electricity, the kind you already know from socks on carpet and staticky hair, because it turns out that mysterious feeling is actually one of the gentlest, most direct ways to feel what an electric charge really is. Then, slowly, over the sections that follow, we will build our way up to electric current, which is really just a very organized, very cooperative flow, something closer to a bucket brigade passing water hand to hand than a single thing rushing from place to place. We will talk about what a circuit actually is, and why it has to form a complete loop, the way a train track has to connect all the way around before a train can keep moving along it. We will talk about voltage and resistance, two ideas that sound intimidating but that map, surprisingly well, onto things you already understand, like the pressure of water in a hose or the narrowness of a pipe that water is being pushed through. We will meet a few of the people who figured these things out, slowly, by candlelight sometimes, through failed experiments and lucky accidents and years of quiet, obsessive tinkering, because the story of electricity is also, unavoidably, a story about specific human beings, with names and workshops and long nights, not some inevitable fact that simply appeared. None of that needs to happen quickly. None of it needs to happen tonight, even. If you fall asleep in the next few minutes, that is a success, not an interruption. This is not a race toward some finish line of understanding. It is closer to a long, slow walk along a coastline in fading light, where the goal was never to reach a particular point before dark, but simply to walk, and to notice what there is to notice, for as long as your eyes stay open, and then to let the rest go. So for now, let your attention rest lightly on this single, strange, quiet fact. Somewhere inside your skull, in this exact moment, tiny signals made of moving charge are still passing this voice along, cell to cell, nerve to nerve, the way a message might pass hand to hand down a long line of people in the dark, each one only needing to pass it to the next. You don't have to do anything to keep that happening. It has been happening since before you could form a single memory, and it will keep happening tonight, on its own, quietly, faithfully, all the way until you're asleep. And it's with that same quiet, patient movement, that same handing of something small from one place to the next, that we're going to begin, in a moment, at the very beginning, with the tiniest pieces of matter there are, and the almost weightless particle inside them that started all of this in the first place. Let's start, then, with something almost too small to imagine, and yet something that every single object around you, right now, is quietly made of. Matter. All matter. The mattress beneath you, the air moving in and out of your lungs, the walls of the room, is built out of atoms. And atoms, as you may already know, in that loose, half-remembered way we know things from school, are built out of even smaller pieces. There is a nucleus at the center, dense and heavy, and around that nucleus there is a kind of soft, shifting cloud of something lighter, something that almost never sits still. Inside that nucleus live particles called protons. Around it, in that restless cloud, live particles called electrons. And here is the first quiet fact worth letting settle into you tonight. The fact that everything else in this whole long story eventually rests on. Protons and electrons each carry something called a charge. Not a charge like a fee you pay, not a charge like a battle, but a property, a kind of built-in tendency, the way a magnet has a tendency to pull toward certain things and push away from others. Protons carry what we call a positive charge. Electrons carry what we call a negative charge, and a proton's positive charge and an electron's negative charge happen to be precisely equal in size, just opposite in nature. One pulls a certain way, the other pulls the opposite way. And when you have equal numbers of each sitting together, their effects cancel out almost perfectly. The way two people pulling on opposite ends of a rope with exactly equal strength leave that rope perfectly still, even though both of them are pulling as hard as they can. That word, positive, and its partner, negative, are not describing anything about good or bad, more or less, better or worse. They are simply labels, names chosen a long time ago to describe two kinds of behavior that are opposite each other. And it is worth pausing on the fact that someone had to choose those particular words at some particular moment, because before that moment, nobody knew to call them anything at all. That someone was, in large part, Benjamin Franklin, in Philadelphia in the 1740s, decades before he ever flew a kite in a thunderstorm, which is a story we'll leave for another night, since it turns out to be both more interesting and less reckless than the version most of us grew up hearing. Franklin was experimenting with static electricity, the kind you can build up by rubbing certain materials together, and he needed some way to describe the two different states he kept observing. Some objects, after being rubbed a certain way, seemed to have a surplus of some invisible something. Others seemed to have a deficit of that same something. Franklin didn't know what that something actually was. Not really. Not the way we do now. He couldn't have known about protons or electrons. Those words, those particles, wouldn't be identified for well over 100 years after his candle had gone out for the night. But he needed language anyway, so he chose the words positive for a surplus and negative for a deficit, the same way you might use those words to describe a bank account with a little extra in it, or one running a little short. And here is where the story takes on a small, quiet irony, the kind that history seems to be full of. Franklin guessed, reasonably, that the invisible something flowing in these experiments moved from the positive side to the negative side, the way water might flow downhill from a fuller container to an emptier one. It was a sensible guess, made with the evidence he had. But it turned out, much later, once physicists could actually study the electron directly, to be backwards. The particles that are actually free to move around in most everyday electrical situations, the electrons, are the negative ones, and they tend to drift from negative regions toward positive ones, not the other way around. Franklin had the direction of the flow reversed, and by the time anyone realized this, the words positive and negative were already so deeply woven into science, into textbooks, into the whole vocabulary people used to talk about these things, that nobody went back to fix it. Scientists simply kept the labels and quietly adjusted their understanding underneath them. So even today, in certain diagrams, certain conventions, you'll find something called conventional current, which is described as flowing from positive to negative, the old Franklin way, even though the electrons doing the actual moving are traveling in the opposite direction. It's a strange little scar left on the language of physics, from a guess made honestly, in good faith, 2.5 centuries ago, by candlelight, with no way of knowing better. You don't need to hold on to that detail. It's just a small, comforting thing to know that even the very language of electricity carries an old mistake inside it, gently, without anyone minding very much. Now, the electron itself wasn't actually identified as a distinct particle until 1897 by a physicist in Cambridge named J.J. Thomson, working with glass tubes and glowing beams and careful, patient measurements of how those beams bent when a magnet was brought near them. Before Thomson, people already sensed that electricity had something to do with tiny, discrete units, something that came in countable pieces rather than in some smooth, continuous fluid. But Thomson was the one who pinned it down, who showed that inside every atom there was this much smaller, much lighter particle, thousands of times lighter than the atom itself, carrying that negative charge. And a little later, another physicist, Robert Millikan, working with something almost absurdly delicate, tiny droplets of oil suspended in an electric field, measured the actual size of that charge, the precise amount carried by a single electron. He did this, by the way, sitting in a dim room for hours at a time, watching individual droplets through a telescope, timing how they rose and fell as he adjusted the electric field around them, patient in a way that feels almost unimaginable now, in a world of instant answers. It is a strange thing to consider that someone once spent so many quiet hours simply watching oil drift in order to understand something you are carrying in trillions of tiny working copies inside your own body at this very moment. So, charge, then, is simply this: a fundamental property that certain particles carry, positive in protons, negative in electrons, and it's the interaction between these two, the pulling together of opposites and the pushing apart of likes, that underlies essentially everything we mean when we casually say the word electricity. And that's actually worth sitting with for a moment, because that one word, electricity, the word we use so easily, so constantly, in ordinary conversation, is quietly covering up several different, related but distinct ideas. The way the word love covers everything from the feeling for a sibling, to the feeling for a partner, to the feeling for a favorite old sweater. When you flip a light switch, you're dealing with charge in motion, a steady flow of electrons moving through a wire. When you touch a doorknob after walking across a carpeted room in wool socks and feel that small, sharp spark, you're dealing with charge that has built up, stayed still for a while, and then suddenly released itself all at once, which is a different situation entirely, even though we call both of these things electricity without a second thought. When lightning cracks open the sky during a summer storm, that too is charge, but charge on an almost unimaginable scale, built up slowly inside a churning cloud and then discharged in a single, violent instant. 3 different situations, 3 different rhythms, one borrowed word trying to hold all of them at once. And that, gently, quietly, is where we'll go next, into the difference between charge that sits still and charge that moves, because it turns out that distinction, still or moving, is one of the simplest and most useful doors into everything else electricity has to teach us, and it's a door we can walk through slowly, without any hurry at all. Let's stay with that doorknob spark for a while, because it's a small, everyday miracle that most of us walk past 100 times without ever really looking at it. You've felt it, maybe on a dry winter evening, maybe in a house with thick carpet and the heater running, drying the air until it feels almost brittle. You shuffle across the room in socks, not thinking about it at all, and then you reach for a doorknob or a light switch, or maybe just to touch someone's arm, and there it is, that tiny, startling snap, a little blue thread of light so brief you're not even sure you saw it, and a sting that makes you pull your hand back before you've decided to. It's such a small thing, it lasts a fraction of a second, and yet inside that fraction of a second is a complete, elegant story about how charge behaves, one that unfolds in 3 quiet acts, if you slow it down enough to watch. The first act happens while you're walking, and it happens so gradually that your body has no way of sensing it. Every material, it turns out, holds onto its electrons with a different degree of firmness. Some materials are almost stingy with them, gripping their electrons tightly, reluctant to let any wander off. Others are more generous, or perhaps just more careless, holding their electrons more loosely, willing to part with a few if something rubs against them the right way. Wool, as it happens, tends to be one of the generous ones. It gives up electrons fairly easily. And carpet, especially synthetic carpet, tends to be one of the stingy ones, an eager acceptor, happy to take on more electrons than it started with. So when the wool fibers of your sock brush against the fibers of the carpet, over and over, with every single step, something small and almost accidental keeps happening at the point of contact. A few electrons, just a few, hop from the wool onto the carpet. Not because anyone intends for this to happen, not because the carpet reaches out and grabs them. It's closer to two surfaces meeting, and one of them, chemically, simply being a slightly better home for a stray electron than the other. And once that electron makes the jump, it doesn't jump back, because the carpet's fibers hold on now, at least for a little while, at least until something changes the arrangement again. One footstep does almost nothing on its own. The number of electrons transferred in a single moment of contact is genuinely tiny, far too small to notice by any of your senses. But you don't take one step, you take dozens, walking from the kitchen to the hallway to the living room, and every single step is another small transaction, another small transfer, and these transactions add up the way small transactions always do, quietly, without ceremony, until suddenly they don't feel small anymore. By the time you've crossed the room, your body, believe it or not, is carrying a real surplus of negative charge. Not a large one in any absolute sense, nothing you could measure with your bathroom scale or feel as any kind of weight, but a real, physical imbalance nonetheless, an actual, measurable crowd of extra electrons distributed across you, all with nowhere in particular to go, all with nothing so far to release them. This is the part worth sitting with, because it explains something that seems almost magical when you first notice it as a child, which is the way your hair can rise. You may have seen this happen to yourself, or to a sibling, standing near one of those big plastic playground slides, or fresh off a wool blanket on a dry day, hair lifting gently away from the scalp, strand by strand, reaching outward as if trying to escape the head it's attached to. It looks like something out of a cartoon, and it feels, honestly, a little bit eerie the first time you catch it happening to you in a mirror. But it's the very same story we've just been telling, just made visible. If your body has picked up a surplus of electrons, and that surplus spreads itself out, as charge of the same sign always tries to do, then every single strand of hair on your head ends up carrying a bit of that same negative charge. And remember the fundamental rule we talked about before, the one that governs everything charge does. Like charges repel each other. They push apart. They do not want to be near each other if they can help it. So each strand of hair, carrying the same negative charge as its neighbors, tries to get as far away from those neighbors as it possibly can. And since each strand is anchored at the scalp, held in place at one end, the only direction left for it to move is outward and upward, away from all the other strands doing the exact same thing at the exact same moment. The result is that soft, standing halo you sometimes see, hair reaching for the ceiling, not because of any pull from above, but because of a push from below, every strand fleeing its identical neighbors in every direction it can find. It's a small, harmless demonstration of a genuinely important idea, which is that charge doesn't have to move to have an effect. It can simply sit somewhere, gathered, waiting, and rearrange the world around it just by being present. Scientists have a name for this waiting kind of charge, a name we touched on before, but is worth returning to now that we have a real, felt example in front of us. static electricity. Static simply meaning still, unmoving, charge that has separated from its usual partner and is, for the moment, staying put. And staying put is really the key word, because it tells you that static electricity isn't some separate, exotic kind of electricity, different in kind from what flows through the wires in your walls. It's the exact same electrons, behaving according to the exact same rule of attraction and repulsion, just caught in a moment of stillness rather than a moment of motion. Which brings us gently back to the doorknob and to the second act of our small story, the act where that stillness finally breaks. Because charge doesn't like to stay separated forever. Not really. It's a bit like water building up behind a dam, patient for a while, but always looking, at some level, for the lowest available path back to balance. All those extra electrons sitting on your skin are looking, in a sense, for somewhere to go, somewhere with fewer electrons already crowded onto it, somewhere they'd be more welcome. And a metal doorknob, it turns out, is an excellent candidate. Metals are unusually generous conductors, materials whose outer electrons aren't tightly bound to any one atom at all, but instead drift rather freely through the whole structure, ready to accept newcomers or send others on their way, with very little resistance. So the instant your fingertip gets close enough to that doorknob, close enough that the air between you can no longer keep the two apart, all those crowded electrons take their opportunity at once, not one at a time, politely, but in a sudden, tiny rush, jumping the remaining gap through the air itself in a single dramatic instant. That is the spark. That is the snap. That's the sting. It's not really the doorknob doing anything to you at all. It's simply your own gathered charge, finally, suddenly, correcting itself, returning to balance in the fastest way it can find, which happens to pass, for one brief moment, straight through the nerve endings in your fingertip on its way there. And once that spark has happened, once the transfer is complete, everything settles. Your body goes back to something close to neutral. The doorknob absorbs the surplus and lets it spread harmlessly into whatever it's connected to, and the whole quiet drama, gathered over dozens of footsteps, resolves itself in less time than it takes to blink. It's a strange thing to realize, lying here now, that this same restless tendency toward balance, this same reluctance in charge to remain separated once a path opens up, is not only behind that small household spark, but behind something far larger, far louder, something that gathers not across a single body walking across a room, but across the entire churning body of a storm cloud. But let's leave the storm cloud waiting there for now, gathering in the dark, because before we can understand how something so vast could behave like a doorknob and a fingertip on a much grander scale, we need to slow down and look at something even more basic. Something so basic, it's easy to walk right past it without noticing. And that's the question of how two charges, sitting apart from each other, with nothing touching, no wire, no spark yet, no contact of any kind, manage to feel each other at all. How does one electron, sitting quietly on your sweater, know that another electron is nearby on the doorknob, or missing from it, before anything has actually jumped the gap? What exactly is doing the feeling, the reaching, the sensing, across empty space? This puzzled people for a long time, and it's worth sitting with that puzzlement rather than rushing past it, because the answer, once you have it, becomes so ordinary that it's easy to forget how strange the question really was. For centuries, the natural instinct was to assume that if two things affect each other, something has to be physically connecting them. Pushes and pulls, in the world as most people experienced it, required contact. You push a cart because your hands are on it. You pull a rope because your fingers are wrapped around it. Action at a distance, some force reaching across open space with nothing in between, felt almost like magic, and serious thinkers were uncomfortable with it. Newton himself, describing how the sun tugs at the earth across the emptiness between them, admitted that the idea of one body acting on another through a void, without anything mediating that action, seemed to him, in his own words, so great an absurdity that he didn't think any competent thinker could ever fall into it. And yet the tug was there. The moon kept orbiting. The apple kept falling. Something was happening across that gap, whether or not anyone had a comfortable way to picture it. Electric charges presented the same puzzle, only smaller, closer, more immediate, something you could produce yourself with a bit of amber and a scrap of wool, long before anyone understood what an electron even was. The ancient Greeks noticed that rubbed amber could lift small bits of straw and feather without touching them, and the word we still use, electricity, actually comes from electron, their word for amber. For thousands of years after that observation, people accumulated more examples of the same basic mystery. Two charged objects, brought near each other, would either lurch toward one another or push firmly apart, and no one could point to the thread or the rod or the hand that was doing the pulling or the pushing. The effect was completely real and completely invisible at the same time. It was a French physicist named Charles-Augustin de Coulomb who, in the 1780s, worked out something remarkably precise about this invisible push and pull, even without knowing what was actually reaching across the gap. He built an extraordinarily delicate instrument, a thin fiber suspending a horizontal rod, with a charged ball on one end balanced by a counterweight on the other, all of it sensitive enough to twist by the tiniest amount when another charged ball was brought close. By measuring exactly how much that fiber twisted at different distances, Coulomb figured out that the force between two charges grows weaker in a very specific way as they move apart. Weaker not in simple proportion to the distance, but to the square of it. Move twice as far away, and the pull or push doesn't just cut in half, it drops to a quarter. Move 3 times as far, and it drops to a ninth. It's the same mathematical pattern, as it happens, that governs how gravity weakens with distance, and also how light spreads out and dims as it travels away from its source, thinning across an ever-expanding sphere of space. Coulomb had no way of explaining why charge should behave this way. He simply measured it, carefully, patiently, twist by twist, and handed later generations a rule that turned out to be exactly right. But a rule is not the same as an explanation, and the deeper question, what is actually reaching across that empty space between the two balls on Coulomb's twisting fiber, remained open for decades longer. The person who finally offered a genuinely satisfying way to picture it was Michael Faraday, an Englishman who had begun his working life binding books rather than studying physics in any formal way, and who taught himself an enormous amount simply by reading the volumes that passed through his hands at the shop where he worked as a boy. Faraday had an unusual gift for thinking in pictures rather than equations, and where others saw a mysterious force leaping across nothingness, Faraday proposed instead that the space itself was not really empty at all. He imagined that every charge, simply by existing, fills the space around it with something, a kind of permanent state of readiness, an invisible structure reaching outward in every direction, which he called a field. Bring a second charge into that space, anywhere within reach of the field, and it doesn't have to wait for some force to travel instantaneously across the gap. It simply responds to the field it finds itself sitting inside, the way a leaf floating on a pond responds to the ripples already moving through the water around it, rather than to the stone that caused them far away. It's a small shift in picture, but it changes everything about how comfortable the idea feels. Instead of asking how one charge reaches all the way across space to grab another, you can instead ask, more simply, What does the space around a charge actually feel like at any given point? And then ask how a second charge would respond to finding itself there. Faraday liked to make this field visible in a rough way using iron filings scattered on a sheet of paper held over a magnet, and if you've ever done this yourself, or seen it done, you'll remember how the tiny metal flecks snap into curved lines the instant the magnet is beneath them, tracing arcs that sweep from one end of the magnet to the other, revealing a structure that was there in the space the whole time, utterly invisible until something was scattered into it and allowed to respond. Electric fields work on the same principle, even though we can't sprinkle anything quite so simple to reveal them. Every charged object, whether it's a single stray electron on your sweater or the charged ball on Coulomb's fiber, sits at the center of its own quiet field, spreading outward in every direction, weakening with distance in exactly that pattern Coulomb had measured, growing fainter and fainter the farther out you travel, but never actually reaching zero, technically extending forever, thinner and thinner, like ripples that never quite disappear, even long after the stone that made them has settled to the bottom. And here is the part worth turning over slowly before we go further. A field, in this sense, isn't a force exactly. It's more like a standing possibility of force, a kind of permanent tension held in the space around a charge, waiting for something else to arrive and feel it. Two positive charges sitting near each other each fill the space around themselves with fields that, where they overlap, push outward against one another, urging both charges apart. The same way two people leaning against each other from opposite sides will each feel the other's resistance without either one needing to reach out and shove. A positive charge and a negative charge, on the other hand, create fields that lean the opposite way, drawing inward, urging the two together, wanting, in a sense, to close the distance and cancel each other out. This is the invisible architecture sitting underneath everything we've talked about so far, underneath the electrons crowding onto your sweater, underneath the spark at the doorknob, underneath even the vast gathering charge inside a storm cloud we set aside a moment ago. None of it required touching. All of it was fields, quietly filling the space between charges, long before anything visible ever happened, waiting patiently for a path to open, for a fingertip to get close enough, for the balance to finally, suddenly, resolve itself. Now, if fields are this quiet tension sitting in space, always ready but not yet resolved, there's a natural question that follows, one that took physicists a surprisingly long time to phrase clearly. If a charge creates this invisible pressure around itself, is there a way to measure how strong that pressure is at any given point, without having to drag another charge around and watch how hard it gets pushed or pulled? It turns out there is, and the answer to that question is what we now call voltage, though the people who first worked this out didn't use that word and wouldn't have recognized much of the language we use to teach it today. Let's sit with the idea slowly, because it's one of those concepts that sounds simple once you have it, and strangely slippery right up until the moment it clicks. Picture, for a moment, a hill, not a particularly dramatic one, just a gentle, grassy slope somewhere quiet, the kind you might walk up without thinking too hard about it. Now imagine a smooth stone sitting near the top of that hill. The stone isn't moving. Nothing about it looks eventful, but if you nudge it, even slightly, it will begin to roll downward, gathering speed as it goes, and it will keep rolling until it reaches the bottom, where the ground finally levels out and there's no more slope left to carry it forward. What made the stone roll wasn't some force reaching out and grabbing it from below. It was simply the shape of the hill itself. The fact that the top of the hill and the bottom of the hill are not at the same height, and the space between them contains this quiet built-in tendency for anything free to move, to travel from the higher place to the lower one. Physicists have a name for that kind of quiet built-in tendency, and it applies to far more than hills. It's called potential energy, and the important thing to notice is that the number that matters isn't really the height of the stone by itself. It's the difference in height between where the stone is and where it could go. A stone sitting on a small pedestal in a perfectly flat field has very little potential energy, even if the pedestal itself is a few feet off the ground, because there's nowhere lower nearby for it to fall toward. But the same stone, sitting at the very top of a tall cliff, has an enormous amount of potential energy, not because of anything about the stone changing, but because of the sheer difference between where it is and where it might end up. Voltage works on exactly this principle, translated into the language of electric charge instead of gravity. When we talk about the voltage between 2 points, we are never really talking about some absolute quantity sitting at either point alone. We are talking about a difference, the electrical equivalent of comparing the top of the hill to the bottom of it, except what's varying isn't height above the ground, it's electric potential, which is really just a way of describing how much work it would take to move a charge from one point to the other, or equivalently, how much energy that charge would release if it were allowed to travel freely between them. A single point in space, all by itself, doesn't really have a voltage in any meaningful sense, any more than a single spot on a hillside has a height without something to measure it against. It's only when you compare 2 points that the idea starts to mean anything at all. This is worth pausing on, because it's easy to slide past it and start thinking of voltage as some kind of electrical stuff, a quantity a battery simply contains, the way a bottle contains water. That's not quite right, though it's an understandable mistake, since we talk about batteries having 9 volts or a wall outlet providing 120 volts as though voltage were a possession, a thing sitting there on a shelf. What's really being described every single time is a difference between 2 points, usually the 2 terminals of the battery, or the 2 slots of the outlet, or the 2 wires running to a lamp. The number tells you how steep the electrical hill is between those 2 points, how strong the tendency is for charge to want to flow from one to the other if given the chance, in exactly the way the steepness of a real hill tells you how eagerly a stone will roll down it once you let go. There's another everyday image that can sit alongside the hill, and it's worth introducing carefully, because analogies for electricity have a tendency to be stretched further than they can really hold, and pressure is one that people lean on often, sometimes past its useful limit. Still, gently, without asking too much of it, think about water pressure in a pipe. If you have a tank of water sitting up on a tower and a pipe running down from it into your house, the water at the top of the tower is under a certain amount of pressure simply because of how high it sits above the tap where the water eventually comes out. Open the tap and the water rushes through the pipe, driven not by anything pushing it from behind exactly, but by that difference in pressure between the top of the tower and the opening at the bottom. Turn the tap off, and the pressure is still there, still waiting, even though no water is currently moving. The water isn't going anywhere until there's a path for it to follow, but the tendency, the readiness, doesn't disappear just because nothing is currently flowing. Voltage behaves a little like that pressure difference, and it's a genuinely useful way to get an intuitive feel for what a voltage is doing, so long as you remember it's an analogy and not a literal description, because charge isn't water, and wires aren't quite pipes, and electric fields don't work by anything physically squeezing. But the shape of the idea translates surprisingly well. A battery sitting on a table, not connected to anything, is a little like that water tower, full of pressure, full of built-up difference between its 2 terminals, entirely ready to push charge through a circuit the instant a path opens up, and yet, with no path available, nothing is moving at all. The moment you connect a wire between the two terminals, giving the charge somewhere to go, that pent-up difference starts to resolve itself, and current begins to flow, much like water rushing downhill or down a suddenly opened pipe, driven along by the very difference that had been sitting there quietly the entire time. It's worth noticing, too, that just like the stone on the hillside or the water in the tower, voltage doesn't actually require anything to be moving in order to exist. This is one of the places where people sometimes get tangled, imagining that voltage is somehow made of motion, but it isn't. A battery sitting untouched in a drawer for years still has its full voltage between its terminals, the same way a stone, perched at the top of a cliff, still has its potential energy even while it's sitting perfectly still, waiting. The difference is there, built into the arrangement of charges inside the battery, long before anything is given the chance to move because of it. What voltage describes is possibility, not action, a kind of stored readiness rather than an event actually taking place. And it's only once a circuit gets completed, once a path opens for the charge to travel along, that the possibility becomes something you can actually watch happen, becomes current, becomes the felt reality of electricity doing something in the world. And once we have that picture in place, this notion of difference, of one point on an invisible landscape sitting higher than another, waiting for a path to open, we're finally ready to ask, what happens when that path does open, when charge is actually given somewhere to travel, and starts flowing at last? So let's start with the question most people never think to ask, because the answer seems so obvious they never even notice there's a puzzle hiding underneath it. When you flip a switch and a lamp across the room turns on almost instantly, what exactly is happening inside that wire? The intuitive picture, the one almost everyone carries around without ever examining it, is that somewhere inside the switch, a gate opens, and a horde of electrons that had been waiting patiently near the switch suddenly go sprinting down the wire, racing across the room at tremendous speed, and arrive at the lamp just in time to make it glow. It feels like a reasonable story. It even fits the timing, since the light really does seem to come on the instant you flip the switch, so surely something must be moving that fast. But this picture, comforting as it is, turns out to be almost entirely wrong, and untangling why is one of the more satisfying corrections available in all of basic physics. Here is the actual situation, and it might help to imagine, before we even get to wires, something much more familiar. Picture a garden hose lying across a lawn, already completely full of water from end to end. No air gaps anywhere inside it. Now imagine you turn on the spigot at one end. Does the water need to travel the entire length of the hose before anything happens at the far end? No, of course not. The instant you open that spigot, water begins to spurt out the other end almost immediately, even though no individual drop of water actually traveled the whole length of the hose in that brief moment. What happened instead is that the new water, pushed in at one end, nudged the water already in front of it, which nudged the water in front of that, and so on. A wave of pressure traveling down the length of the hose far faster than any single molecule of water was actually moving. The molecules themselves might be drifting along quite slowly, but the push, the pressure change, propagates practically all at once. A wire full of electrons behaves in a strikingly similar way, and this turns out to be the key that unlocks the whole confusion. A copper wire isn't like an empty highway waiting for cars to be let onto it. It's already absolutely packed with electrons, every single atom of copper contributing its share, sitting shoulder to shoulder throughout the entire length of the wire, whether the switch is on or off. There's no waiting room of electrons bunched up near the switch, ready to be released. They're already everywhere along the wire, all the time, in roughly the same numbers whether current is flowing or not. What the switch actually does, when you close it, is complete a circuit and allow an electric field to establish itself along the entire length of the wire. And that field is the thing that moves fast, remarkably fast, propagating through the wire at a sizable fraction of the speed of light. Every electron in the wire, from the switch all the way to the lamp, feels that field arrive and begins to shift in response to it at very nearly the same moment. It's not that one electron sprints the distance. It's that the entire population of electrons, already present the whole length of the wire, gets nudged into motion almost simultaneously, the way every water molecule in that already full hose gets nudged forward the instant you open the spigot. So the light really does turn on almost instantly, and your intuition about the timing was correct all along. What was wrong was the idea about what was actually racing across the room. It wasn't electrons. It was the field, the influence, the invisible nudge that tells electrons everywhere in the circuit, more or less all at once, that it's time to start drifting. And this brings us to the part that tends to surprise people the most, the part that seems almost too strange to be true until you sit with it for a moment. The electrons themselves, the actual particles doing the moving once that field arrives, drift along unbelievably slowly. Not fast, not even moderately fast. Slowly, in a way that would be almost comic if you pictured it happening with anything else. In a typical household wire, carrying a typical amount of current, the average electron drifts along at something on the order of a few centimeters per minute. Some rough estimates put it even slower than that, depending on the wire's thickness and the current involved. But the general scale holds. We are talking about speeds you could easily outpace by watching a snail amble across a garden path, or by observing the minute hand crawl around the face of a clock. If you could somehow paint a single electron a bright color and watch it travel from your wall switch to the light fixture 8 feet away, you might be waiting the better part of an hour, or even longer, to see it complete that short journey, drifting along in fits and starts, constantly bumping into copper atoms, constantly getting knocked sideways and backward before shuffling forward again. Net progress achingly slow despite the light bulb overhead having switched on in a fraction of a second. This distinction between the speed of the individual charges and the speed of the signal telling them to move has a nice historical echo in the way people first thought about long-distance electrical communication, back when telegraph engineers in the middle of the 19th century were stringing wires across continents and beneath oceans. Some of the early telegraph theorists actually worried, quite seriously, that a signal sent across thousands of miles of undersea cable might blur and smear out along the way, arriving as an indecipherable mess rather than a crisp series of pulses, because they weren't yet sure how to separate the idea of the signal traveling from the idea of the charge itself physically making that entire journey. It took careful mathematical work, including contributions from physicists working through the equations governing how fields propagate along conductors, to properly separate these two things, the fast-moving disturbance and the slow-drifting charge carriers, and to show that a signal really could race down a wire at a healthy fraction of light speed, even while the material of the wire itself, and the electrons within it, went nowhere very quickly at all. It helps, maybe, to reach for one more everyday image before we move on, since these ideas tend to settle in better with something familiar to hold on to while drifting toward sleep. Think of a long line of people standing shoulder to shoulder, all the way down a hallway, each person able to nudge the shoulder of the person just ahead of them. If the person at the very back of the line gives a gentle push, That nudge travels down the line remarkably quickly, shoulder to shoulder, reaching the front of the hallway in moments, even though no individual person walked the length of the hallway to deliver it. Each person moved only a tiny amount, barely shifting their weight forward before settling again, and yet the nudge itself arrived at the far end almost instantly. That's something close to what's happening inside a wire, a chain of already present charges, each one shifting only slightly, passing along an influence that moves through the whole system far faster than any one of them personally travels. And once we've settled that distinction, the field arriving in an instant, the charges themselves creeping along at something closer to a snail's unhurried pace, there's a natural next question waiting quietly just behind it. The question of how much of that drifting charge is actually needed to make a light bulb glow, or a motor spin, or anything else in the world of electricity happen at all. That question about how much drifting charge is needed leads somewhere interesting, because the answer depends entirely on how easily that charge can move through whatever material it's traveling through, and that ease of movement, or lack of it, turns out to be one of the most practical ideas in the whole subject of electricity. It has a name, resistance, and understanding it properly means slowing down again, the way we've been slowing down all along, to look closely at something that seems simple on the surface, but rewards patience. Picture that hallway once more, the long line of people passing a nudge from one shoulder to the next. Now imagine the hallway isn't empty. Imagine there are obstacles scattered along its length, maybe some furniture nobody bothered to move, or a floor that's uneven in places, sticky in others. Passing that nudge down the line becomes harder. People bump into things. Some of the energy of the nudge gets absorbed by those collisions, turned into small jostles and bumps rather than passed cleanly forward. The hallway still works. The nudge still gets through eventually, but it takes more effort, and something is lost along the way, dissipated into the obstacles themselves, rather than delivered cleanly to the far end. That, in a rough and friendly sort of way, is what resistance is inside a wire. The electrons drifting through a conductor aren't moving through empty space. They're moving through a lattice of atoms, a three-dimensional structure of atomic nuclei, each one sitting in place, each one's vibrating slightly with whatever thermal energy the material happens to have. And as the electrons drift along, nudged forward by the electric field, they don't glide through this lattice unobstructed. They collide with it, not constantly, not violently, but often enough, colliding with atoms, scattering off imperfections in the metal, bumping into impurities that don't quite belong in the crystal structure, losing a little bit of their forward momentum with nearly every collision before the field nudges them onward again. Every one of those tiny collisions does something. It transfers a small amount of energy from the moving electron into the vibrating lattice of atoms around it. And what does it mean, physically, for atoms to vibrate more? It means the material has gotten warmer. This is, at the most basic level, why wires heat up when current flows through them. It isn't magic, and it isn't some strange side effect that appears only in special circumstances. It is simply what happens whenever moving charge has to push its way through a material that offers resistance to that motion. Some of the electrical energy being carried by the moving electrons gets converted, collision by collision, into heat, warming the wire itself, sometimes so gently it's imperceptible, sometimes enough to glow. This turns out to be exactly the principle behind the incandescent light bulb, at least in its classic and now largely retired form. A thin filament, originally made from carbonized bamboo fiber by Thomas Edison's team in the autumn of 1879, later refined into tungsten filaments that could survive far higher temperatures without breaking down, offers a great deal of resistance to the current pushed through it. That resistance means a great many collisions between drifting electrons and the atoms of the filament, and all those collisions generate heat, so much heat, packed into such a thin and enclosed space that the filament glows white hot, radiating light along with all that warmth. The same basic phenomenon in a toaster's heating element or the coil inside an electric kettle is put to work quite deliberately. Resistance harnessed on purpose to produce heat exactly where it's wanted. But resistance isn't always so welcome. In the long copper wires that carry electricity from power plants to homes, resistance is mostly just a nuisance, a source of wasted energy. Electricity converted into heat that simply radiates uselessly out into the open air along the length of a transmission line, energy that never makes it to anyone's lamp or refrigerator. This is part of why power companies favor transmitting electricity at very high voltages and comparatively low currents, since, as we'll get to more fully later, the heat lost to resistance in a wire depends heavily on how much current is flowing through it, and keeping current low, while voltage carries the energy, instead helps limit how much gets wasted along the way as unwanted warmth. Not every material resists the flow of charge equally, and this is worth sitting with for a moment, because it explains so much about why certain materials get chosen for certain jobs. Copper and silver are unusually good conductors, their atomic structure allowing electrons to drift with relatively few collisions, which is why copper wiring fills the walls of most buildings, and silver, more expensive but even more conductive, shows up in specialized electronics, where every fraction of resistance matters. Materials like rubber and glass, on the other hand, resist the flow of charge so strongly that for most practical purposes, they simply don't conduct electricity at all, under ordinary conditions, which is exactly why they're used as insulation, wrapped around wires to keep the current safely contained, rather than wandering off into whatever happens to be nearby. And then there are materials, like the nickel-chromium alloy called nichrome, chosen deliberately for having moderate resistance, high enough to generate useful heat, but able to withstand that heat without melting or breaking down, which is why nichrome wire shows up coiled inside toasters and space heaters and hair dryers, doing its resistive work quietly for years. All of this brings us, gently, to a relationship that a Bavarian physicist named Georg Simon Ohm worked out in the 1820s, publishing his findings in 1827 after years of careful, painstaking experimentation with wires of different lengths and thicknesses, measuring how the current flowing through them changed as he varied the voltage applied across their ends. His work wasn't warmly received at first. It was considered, by some of his contemporaries, a bit too mechanical, too reliant on treating electricity like a fluid governed by simple mathematical rules rather than something more mysterious. Ohm lost his teaching position for a time, and it would be years before the scientific community came around to recognizing what he'd actually discovered, a recognition that eventually included the Royal Society awarding him the Copley Medal in 1841, and later, the unit of electrical resistance itself being named the ohm in his honor. What he found was this: for many materials, especially metals, at a fairly constant temperature, the current flowing through them is directly proportional to the voltage pushing them, and inversely proportional to the resistance standing in the way. Double the voltage and you double the current. Double the resistance and you cut the current in half. It's often written as a small equation: current equals voltage divided by resistance, though there's no need to hold on to the symbols themselves tonight, only the relationship they describe. And that relationship maps rather naturally onto the plumbing image we've leaned on before. Voltage is something like water pressure, the force pushing water through a pipe. Current is something like the actual flow of water, the amount passing a given point each second. And resistance in this picture is something like the narrowness of the pipe itself, or the roughness of its interior walls, however much friction stands between the water and its free movement forward. A wide, smooth pipe offers little resistance, and even modest pressure produces a strong flow. A narrow, cluttered pipe offers a great deal of resistance, and even considerable pressure struggles to push much water through it at all. Squeeze the pipe further, add more obstacles, and the flow drops even with the same pressure behind it. Ease off, widen the path, and the same pressure suddenly pushes far more water through. This simple relationship, quiet and elegant once you sit with it, ties together the three ideas we've now spent so long getting comfortable with, one at a time: the pressure of voltage, the flow of current, and the friction of resistance, each shaping the others in a way that governs nearly every circuit ever built. And once those three ideas are resting together comfortably in mind, there's a natural place to go next, toward the question of what happens when we start connecting things, one after another, or side by side, and how a circuit's overall behavior depends on the paths we give the current to follow. But before we follow current down the branching paths of circuits, it's worth pausing on something that quietly sits underneath all of this, something we've been assuming rather than explaining. Why does a copper wire let electrons wander through it so easily, while the rubber sleeve wrapped around that same wire stops them cold? We've talked about resistance as though it were simply a dial, turned up or down depending on how narrow or cluttered a pipe might be. But the truth is that different materials aren't just slightly more or less resistant to current, the way a slightly narrower pipe might slow water down. They belong to entirely different categories of behavior, and the reason has to do with something happening at a scale far too small to see, down among the atoms themselves. Picture, for a moment, the inside of a chunk of copper, the same reddish metal that makes up so much of the wiring tucked behind the walls around you right now. Copper atoms, like all atoms, are built from a dense little nucleus at the center, and a cloud of electrons arranged around it in layers, rather like the layers of an onion, though nothing so neat and orderly as concentric circles. The electrons closest to the nucleus are held tightly, bound by a strong pull toward the positive charge at the center, the way a small child holds a parent's hand in a crowded space, unwilling to let go. But the electrons in the outermost layer are a different story entirely. They sit at the edge of the atom's influence, far enough from the nucleus that its grip on them has grown weak, almost negligent. In an isolated atom, floating alone in empty space, even those outer electrons would still belong to their nucleus, however loosely. But copper atoms are never alone. They sit packed together in a solid, shoulder-to-shoulder, trillions upon trillions of them arranged in a repeating lattice, an orderly, three-dimensional pattern that looks, if you could shrink yourself down and wander through it, something like a vast and endlessly repeating scaffold. And it's within that shared scaffold that something remarkable happens. Each copper atom's outermost electron finds itself close enough to the neighboring atoms that its allegiance becomes ambiguous. It's no longer clear which nucleus it belongs to, because in a sense it belongs to all of them, and none of them, at once. These outer electrons stop behaving like private property and start behaving like a shared resource, a kind of communal fluid that flows freely through the entire lattice of atoms, unattached to any single one. Physicists sometimes call this a sea of electrons, and it's a good image to hold on to, because it captures something true about the freedom involved. The electrons aren't clinging tightly to their home atoms anymore. They're drifting loosely through the whole structure, like a crowd of people milling about a large open room rather than sitting fixed in assigned seats. This is the essential feature of a conductor, and it's worth sitting with, because it explains so much of what follows. When you attach a battery to a copper wire, you're not somehow injecting new electrons into the metal that weren't there before. The electrons were already present, already loosely drifting through that shared sea, long before you connected anything at all. What the battery does is apply a gentle, steady push, an electric field running the length of the wire, nudging that entire sea of loose electrons to drift in one general direction rather than wandering randomly this way and that. It's a bit like a crowd of people standing around in a large room, shifting their weight, chatting, moving idly in no particular pattern, until someone opens a door at one end and announces that lunch is being served in the room next door. Suddenly, there's a gentle overall drift toward that door, though people are still bumping into each other, still moving somewhat randomly on the small scale. The collective motion now leans in a single direction. That's very much what current looks like inside a copper wire. A slow overall drift of an enormous population of loosely held electrons, riding on top of much faster, much more chaotic individual jostling. Now hold that picture beside a very different material, the rubber that insulates a wire, or the plastic casing around a plug, or the glass in a window. Rubber is built from very different atoms arranged in a very different way, largely carbon and hydrogen, bound together into long chain-like molecules that tangle and coil around each other like cooked spaghetti left to cool in a pot. And in these molecules, the outer electrons are not loose and communal at all. They're tightly bound into specific chemical bonds, each electron pair locked between two particular atoms, holding those atoms together the way a firm handshake holds two people in place. There's no shared sea here, no loose crowd milling freely through the material. Every electron has a specific job to do, a specific bond to maintain, and it stays put, because the energy required to pull it free from that bond is far larger than anything in ordinary voltage, the kind found in household wiring, or even a small spark, could ever hope to supply. This is what makes rubber, and materials like it, insulators rather than conductors. It's not that rubber has no electrons at all. That would be impossible, since electrons are woven into the structure of every atom in existence. It's that rubber's electrons are all spoken for, all locked into fixed positions, with no loose population left over to drift and carry current the way copper's outer electrons do. Apply a voltage across a piece of rubber, and you're pushing against a material that simply has nothing free to move. It's a little like trying to start a crowd flowing toward a door in a room where everyone is already tied down to a chair, bolted firmly to the floor. The push might be there, the announcement of lunch might ring out just as clearly, but nobody can actually go anywhere, because nobody is free to move in the first place. There's something wonderfully symmetrical hidden inside this comparison, if you think about it slowly enough on a quiet night like this one. Two materials, copper and rubber, are both made of atoms, both made of electrons and nuclei, following the very same laws of physics, obeying the very same rules of electric attraction and repulsion, and yet one behaves like an open highway for electric current, and the other behaves like a solid wall. The difference isn't some special ingredient present in one and absent in the other. It's a difference in arrangement, in how tightly or loosely the outermost electrons happen to be bound within each particular structure. Nature didn't design copper to be a conductor and rubber to be an insulator, in the sense of building them for that specific purpose. It simply happened that the atomic architecture of metals like copper produces this loose, shared sea of electrons, while the atomic architecture of long-chain molecules like rubber locks every electron into a fixed, immovable position. We noticed the consequence, the willingness or unwillingness to carry current, long before we understood the underlying cause, and it took a great deal of patient scientific work across many decades to trace that visible behavior back down to this quiet, invisible difference in how electrons are held. It's worth noting, too, before we drift onward, that this isn't a simple binary split between two tidy categories, however convenient that might be for a bedtime story. There's a whole spectrum of behavior in between, materials that conduct somewhat under the right conditions without ever behaving quite like copper or quite like rubber. Some materials sit right at the boundary, nudged one way or the other by warmth, or by the addition of tiny impurities scattered through their structure, and it's there, in that in-between territory, that some of the most useful and most curious electrical behavior in the modern world quietly happens to live. But let's set that in-between territory aside for now, and let it rest quietly in the back of your mind, because there's a more immediate question worth drifting toward, one that's been waiting patiently underneath everything we've discussed so far. We've talked about electrons moving, about materials that let them move freely, and materials that hold them still, but we haven't yet asked the simplest question of all. What actually gets those electrons moving in the first place? Where does the push come from? Because electrons, left alone, don't spontaneously organize themselves into an orderly flow. Something has to nudge them. Something has to create the conditions that make a current worth calling a current, rather than just a random, directionless jostling. And for most of us, in daily life, that something is a battery. Picture, if you will, one of the plainest and most familiar objects in the world. A small cylinder, metal on the outside, with a little bump on one end and a flat surface on the other. You've held 1,000 of these in your hand without a second thought, sliding them into flashlights, into remote controls, into toys that beep and hum. And yet inside that unassuming little cylinder is a genuinely strange piece of chemistry, a carefully engineered imbalance that the whole rest of the circuit exists to correct. To understand what's happening inside, it helps to go back, gently, to the story of how batteries were even discovered, because it's a story built on a disagreement between two Italian scientists in the late 18th century, and disagreements, it turns out, can be wonderfully productive things. Luigi Galvani, a physician in Bologna, was dissecting frogs, as physicians and anatomists of his era often did, and he noticed something peculiar. When he touched a frog's leg with two different metals at the same time, a scalpel of one kind of metal and a hook of another, the leg twitched, as though some spark of life had passed through it. Galvani believed he had found evidence of what he called animal electricity, a kind of vital force stored within the tissue of living things themselves, waiting to be released. Alessandro Volta, a physicist working not so far away, found this idea intriguing but not quite convincing. He suspected the truth was more interesting, in its own quiet way, than a hidden life force. He suspected that the frog's leg wasn't the source of the electricity at all, but merely a sensitive detector of it, a kind of biological voltmeter, twitching in response to something happening between the two metals themselves. And so Volta began experimenting, methodically, patiently, stacking discs of different metals, separated by cloth soaked in salty water, building what came to be known as the voltaic pile. And it worked. It produced a steady, continuous electric current, entirely without any frog involved, which told him, quite clearly, that the electricity had come from the chemistry of the metals and the liquid between them, not from any special property of living flesh. This is worth sitting with for a moment, because it's really the seed of everything a battery does, even today, in the sleek little cylinder in your flashlight. Volta had discovered that certain chemical reactions, when arranged just right, naturally want to push electrons from one place to another, not because anyone is forcing them to, but because it is, in a sense, energetically comfortable for them to do so, the the same way water naturally wants to flow downhill without anyone pushing it. Inside a modern battery, there are two different chemical materials, kept carefully apart from each other, usually separated by a paste or a liquid called an electrolyte. One material has a strong tendency to give up electrons. Chemists sometimes describe this material as wanting to oxidize, to lose electrons as part of a reaction it finds favorable. The other material has the opposite tendency. It has a strong appetite for electrons, a chemical hunger to receive them. Left completely alone, sealed inside the battery with no path connecting them, these two materials sit there in a kind of chemical standoff. The electron-giving material wants to give, and the electron-receiving material wants to receive, but there's no route between them, no path for that exchange to actually take place, so nothing happens. The battery, sitting quietly in a drawer, is a coiled spring of chemical potential, patient and unmoving, storing an imbalance that hasn't yet found its release. Now imagine connecting that battery into a circuit, a simple one, nothing more than a wire running from one end of the battery through a small light bulb and back to the other end. The moment that connection completes, the moment the circuit closes into an unbroken loop, everything changes. Suddenly, there is a path. The material that wanted to give up electrons finally has somewhere to send them, out along the wire, and the material that wanted to receive electrons finally has a route by which they can arrive. And electrons, ever willing to follow a path that chemistry has made favorable for them, begin to flow. It helps, maybe, to think of it the way you might think of two rooms in a house, one crowded with people eager to leave, and one nearly empty, welcoming to newcomers, with the two rooms connected only by a single, narrow hallway that has been, until this moment, blocked off. The moment you open that hallway, people begin walking through, not because anyone is hurting them, but because that's simply where the openness and the crowding naturally lead them. Close the hallway again, and the movement stops instantly, even though the crowding and the emptiness in each room haven't changed at all. The potential is still there, waiting, but without the connection, it goes nowhere. This is exactly what a switch does in a real circuit, incidentally, though we'll come back to switches more fully later. For now, it's enough to notice that the wire is the hallway. The battery is the crowded and empty rooms combined into a single compact object, and the flow of electrons through that wire is what we've been calling electric current all along, the same gentle river of charge we spoke of earlier, except now we can see exactly what created the slope for it to flow down. And what about the light bulb sitting in the middle of that wire? As the electrons pass through its thin, resistant filament, they encounter exactly the kind of friction we talked about a little while ago, that gentle traffic congestion of resistance. Atoms in the filament jostling against the moving electrons, and that jostling produces heat, so much heat, in the case of an old-fashioned incandescent bulb, that the filament glows brightly enough to light a room. The energy for that glow, that warm little pool of light spilling across your nightstand, didn't come from nowhere. It came, step by careful step, from a chemical reaction happening quietly inside the battery. A reaction that had been sitting there, coiled and ready, perhaps for months, waiting only for a path to be completed. This is really the heart of what a battery does, when you strip away all the specific chemistry and just look at the underlying idea. It converts one kind of stored energy, chemical energy, locked up in the arrangement of molecules and the willingness or unwillingness of certain atoms to hold on to their electrons, into another kind of energy entirely, the kinetic energy of electrons drifting steadily through a wire, which can then be converted yet again into light or heat, or the quiet spinning of a small motor, or the soft glow of a screen. Energy doesn't vanish and doesn't appear from nowhere in any of this. It simply changes its costume, again and again, chemical to electrical, to whatever form finally does the useful work you were hoping for. And as the reaction inside the battery slowly runs its course, as the electron-giving material gradually depletes its supply and the electron-receiving material gradually fills up, the battery weakens, the light dims, the imbalance evens out, until eventually there's no more push left to give, and the battery, as we say, quite simply, runs down. Now, batteries are wonderful, patient little reservoirs, but they can't be the whole story, because if every bit of electricity in the world had to come from a chemical reaction slowly discharging inside a cylinder of metal and paste, we would run out of usable power almost as quickly as we made it. Somewhere, on a much larger scale, electricity has to be generated continuously, hour after hour, to keep entire cities lit and humming. And the answer to how that happens takes us somewhere you might not expect. It takes us to magnets. At first, electricity and magnetism seem like two completely separate topics, don't they? One is about tiny charged particles drifting through wires, and the other is about the strange, invisible pull that makes a compass needle swing north, or that lets you stick a photograph to the refrigerator door with a small, colorful disc. For a long time, going back centuries, people studied these as though they belonged to entirely different chapters of nature. The Greeks noticed that rubbing amber could attract small bits of straw, and separately, they noticed that certain stones, what we'd now call lodestones, could attract iron and always seemed to point in a particular direction when allowed to swing freely. Two curiosities, filed under two different headings, static electricity in one drawer, magnetism in another, and nobody had much reason to think the drawers were connected. Then, in 1820, a Danish physicist named Hans Christian Ørsted was setting up a rather ordinary lecture demonstration, the kind of thing professors do dozens of times a year, mostly on autopilot. He had a wire connected to a battery, and, quite by chance, he had a small magnetic compass sitting nearby on the table. And when he closed the circuit, when current began to flow through that wire, he noticed something that must have made him stop entirely still for a moment. The compass needle twitched. It swung away from north, as though some invisible hand had reached out and nudged it, and then, when he broke the circuit and the current stopped, the needle swung calmly back to where it had been. Try to imagine what that must have felt like, in that quiet lecture room, watching a needle move for no reason anyone could yet explain, simply because electricity happened to be flowing through a nearby wire. It's the kind of small, strange moment that quietly rearranges an entire field of science. Ørsted had stumbled onto something nobody had properly demonstrated before, that electricity and magnetism were not, in fact, separate phenomena filed in separate drawers at all. They were two expressions of the very same underlying thing. Moving electric charge creates a magnetic field, not sometimes, not under special circumstances, but always, everywhere, any time a current flows. The wire on his table had, without anyone designing it to, become a weak, temporary magnet the instant the circuit closed, and the compass, which had spent its whole existence responding to the great magnetic field of the Earth itself, was simply responding to this much smaller, nearer one instead. If you've ever wrapped a length of insulated wire around a nail, connected the ends to a battery, and used it to pick up paper clips, you've recreated, in miniature, exactly this discovery. The nail itself isn't magnetic on its own, not in any permanent sense, but once current flows through the coiled wire around it, a magnetic field springs into being, threading through the loops of wire and through the metal of the nail, and suddenly it can lift a small scattering of paper clips, as though it had always been capable of such a thing. Disconnect the battery, and the field collapses. The paper clips fall, and the nail goes back to being, magnetically speaking, entirely unremarkable. This connection deepens further when you look closely at what's actually happening around a single wire carrying current, even without any nail or coil involved. If you were to sprinkle iron filings on a flat piece of cardboard with a current-carrying wire poking through it, the filings would arrange themselves into faint concentric circles, rings around the wire, tracing out the invisible magnetic field that the moving charge had created. Each electron drifting along that wire contributes, in its own small way, to that circular field wrapping around the conductor's path. It's not that the electrons are magnetic themselves in any simple sense, though there is a deeper story there, involving something physicists call spin, but rather that their collective motion, charge moving through space, is precisely what a magnetic field is a response to. Now here comes the part that changed the modern world more than almost any other single scientific insight. Because if a moving electric current can create a magnetic field, the reverse turns out to be true as well. A changing magnetic field can create an electric current. This is called electromagnetic induction, and it was worked out carefully, through years of patient experimentation, primarily by an English scientist named Michael Faraday in the early 1830s. Faraday had almost no formal mathematical training, having started his working life as a bookbinder's apprentice with little money and less access to the usual pathways into science. But he had extraordinary patience, an almost meditative willingness to run the same careful experiment slightly differently, over and over, watching closely for what changed. What Faraday discovered, essentially, is this. If you take a loop of wire and hold a magnet perfectly still near it, nothing happens. No current flows, no matter how strong the magnet is. The magnetic field is there, present, real, but static, unmoving, and a static field alone does nothing to the electrons sitting quietly in that wire. But the moment you move the magnet, slide it closer, pull it away, or spin it past the loop, something remarkable happens. A current begins to flow through the wire, for as long as the magnet keeps moving. Stop moving it, and the current stops too. It isn't the magnetic field itself that pushes the electrons along. It's the changing of that field, the fact that its strength, as felt by the wire, is rising or falling from moment to moment. You can picture it, if it helps, a little like the way a boat rocks on still water. If the water is calm and unmoving, the boat simply sits there, undisturbed. But send a wave through that water, some change moving past the boat's hull, and the boat rocks, rises, and falls in response. It isn't the water's mere presence that moves the boat. It's the change happening in that water as it passes by. Faraday's wire loop responds to a changing magnetic field in something like the same way, translating that change into a gentle, steady push on its electrons, a nudge that sends them drifting around the loop as an actual measurable current. This single discovery is the reason that spinning a magnet near a coil of wire, or spinning a coil of wire near a magnet, it works either way, produces electricity continuously for as long as something keeps that spinning going. And this is precisely the principle sitting quietly at the heart of nearly every generator on the planet, whether it's turned by falling water rushing through a dam, or steam pushed by heat from burning coal or splitting atoms, or wind turning the long blades of a turbine out on some open, breezy plain. In every single case, without exception, something mechanical is being used to spin a magnet near a coil, or a coil near a magnet, and that spinning, that continuous changing of the magnetic field as felt by the wire, is what generates the electric current that eventually reaches your home. It's a strange thing to sit with, really, late at night, that the electricity quietly powering the small lamp beside your bed traces back, through wires and transformers and substations, to something spinning somewhere, turned by water or wind or steam, converting motion into a changing magnetic field, and that changing field, reaching into a coil of copper wire, gently nudging electrons into motion. Which brings us, quite naturally, to the question of what that spinning coil actually looks like up close, and how something as simple as motion and magnetism, working together, quietly grew into the very large machines we now call generators. Here's the thing about that spinning coil, the detail that trips people up the first time they really think about it. As the coil turns inside the magnetic field, or the magnet turns around the coil, the wire doesn't experience the field the same way twice in a row. At one moment, a side of the loop is cutting across the field lines quickly, pushing electrons hard in one direction. A quarter turn later, that same side is moving parallel to the field, barely cutting across it at all, and the push fades to nothing. Another quarter turn, and the side of the loop that was moving one way is now moving the opposite way relative to the field, and the push on the electrons reverses entirely. This happens smoothly, continuously, dozens of times each second in a spinning generator, and the result is a current that doesn't flow steadily in one direction the way water flows down a hill. Instead, it rises, falls back to zero, reverses, rises again in the opposite direction, falls back to zero, and reverses once more, over and over, in a smooth, rhythmic wave. This is alternating current, usually just called AC, and it is, quite simply, the natural electrical signature of anything spun to generate power. Contrast that with the electricity stored in a battery, which is direct current, or DC. Inside a battery, a chemical reaction pushes electrons out of one terminal and pulls them back in through the other, and it does this in one direction only, steadily, without any reversing. Plug a small DC device into a battery and the electrons drift one way through the circuit the whole time, from the moment the connection is made until the battery runs down. There's no wave to it, no rising and falling, just a steady, patient flow, like water moving through a pipe under constant pressure. Both kinds of electricity do useful work. Both can light a bulb, spin a motor, warm a wire. But they behave differently enough and are produced differently enough that the choice between them shaped an entire chapter of electrical history, one that unfolded with surprising intensity in the final years of the 19th century. Thomas Edison had built his early power stations around direct current, and he was deeply invested, both financially and personally, in seeing it become the standard for the country. George Westinghouse, backed by the engineering work of Nikola Tesla, was building his systems around alternating current instead. Between them lay a real, practical disagreement, not simply about business, but about physics and distance. Here is the trouble Edison ran into, and it's worth sitting with, because it explains almost everything that follows about how power actually travels to your home tonight. Sending electricity any real distance means pushing it through wires, and wires resist that push. Some of the electrical energy is lost along the way, converted quietly into heat as it fights through the resistance of the metal, and the longer the wire, the more energy is lost. There's a way to reduce that loss, though, and it comes down to a relationship worth holding gently in mind. For a given amount of power delivered, if you raise the voltage, the current can be lowered proportionally, and since the heat lost in a wire depends on the current, not directly on the voltage, sending power at high voltage and low current wastes far less energy over long distances than sending it at low voltage and high current. This is where alternating current had a genuine, decisive advantage in Edison's era. A transformer, a device built from two coils of wire wound near each other around an iron core, can raise or lower the voltage of alternating current quite easily, simply by using different numbers of loops in each coil. relying on that same Faraday principle of a changing magnetic field inducing current. This time, coil to coil rather than magnet to coil. Direct current, steady and unchanging as it is, doesn't produce a changing magnetic field at all, so 19th century transformers simply couldn't do this trick for it. That meant Edison's direct current power stations had to sit close to the buildings they served, within about a mile or so, because sending DC any farther at the voltages practical for lighting a lamp wasted too much power along the way, and stepping the voltage up or down first wasn't something the technology of the day allowed. Alternating current, by contrast, could be generated, stepped up to a very high voltage for the long journey, sent for miles with comparatively little loss, and then stepped back down to something safe by the time it reached a house. Westinghouse and Tesla's approach eventually won out, not through some single dramatic moment, but through this accumulating, practical advantage, and it's why the grid spanning entire countries today runs almost entirely on alternating current. So follow that journey now, slowly, the way electricity itself actually travels. It begins at a generator, that spinning coil or spinning magnet, turned by falling water, or steam, or wind, producing alternating current at a few thousand volts, already more than enough to be dangerous to the touch, but still far too low for efficient long-distance travel. Right there at the power plant, transformers step that voltage up dramatically, sometimes to several 100,000 volts, sending the current down current relatively low, so that the long transmission lines you might glimpse stretching across open countryside, strung between tall steel towers, waste as little energy as possible, carrying power toward distant cities. Those transmission lines eventually reach a substation, often an unassuming fenced lot dotted with humming transformers and switching equipment, easy to drive past without a second glance. Here, the voltage is stepped down, though still to a level far higher than anything found in a home, perhaps down to a few tens of thousands of volts, suitable for distribution across a region rather than crossing an entire state. From the substation, distribution lines carry this somewhat lower voltage electricity out toward neighborhoods, sometimes overhead on the wooden poles lining ordinary streets, sometimes buried underground where the wires are hidden entirely from view. Closer to the actual houses, another transformer takes over, often that gray cylindrical can mounted partway up a utility pole, or a green metal box sitting quietly on a patch of grass near a curb, easy to overlook entirely unless you happen to know what you're looking at. This transformer performs the final step down, bringing the voltage to the roughly couple hundred volts, or in some countries closer to 120, that a home's wiring is actually built to handle. From there, a service line runs to the house itself, entering through a meter that quietly counts how much electrical energy passes through, and then into the home's internal wiring, branching out through the walls to every outlet and switch and fixture. By the time alternating current reaches the outlet beside your bed, it has typically traveled through several transformers, been raised and lowered in voltage more than once, and arrived after passing through generation, transmission, and distribution, a journey that in a single second, the electricity itself covers in a fraction of that second, since it moves through the wires at a significant portion of the speed of light. And still, throughout that entire journey, the current has been reversing direction rhythmically, dozens of times each second, the whole way, arriving at your lamp still oscillating exactly as it did the moment it left the spinning generator, faithfully carrying that rhythm across however many miles separated you from wherever the turning began. It's worth pausing on that rhythm itself for a moment, because it isn't arbitrary. The rate at which that current reverses back and forth settled, over decades of engineering decisions, into standard numbers that different regions still use today, and there's a quiet history behind why some countries settled on one number and others on a slightly different one, a story bound up in early competing equipment and in habits that, once set, proved remarkably difficult to change. In the United States, that number became 60 cycles per second, a figure that traces back, in part, to the practical judgment of early engineers who found it worked well with the generators and motors of the era, striking a workable balance between the size of equipment and the smoothness of the light it produced. In much of Europe, the number that took hold was 50. Neither choice was inevitable. Neither was more correct than the other, in any deep physical sense. They were simply the numbers that different networks of engineers, working somewhat independently, converged on and then built enormous infrastructure around. Infrastructure so vast and so interconnected that changing the number afterward would have meant replacing or adjusting nearly everything downstream of it. And so today, if you were to fly from one continent to another, the electricity waiting for you at your destination would still be alternating, still be carrying that same essential rhythm, just ticking to a very slightly different beat, 60 reversals a second in one place, 50 in another, both too fast for any lamp to visibly flicker, both quietly doing the same fundamental job. It's a small detail in the end, but it's a nice reminder of something that has come up again and again across this whole story, which is that so much of how electricity behaves in your daily life isn't really about the electrons themselves. The electrons don't care whether they're reversing 50 times a second or 60. They don't care whether the wire they're drifting through is copper or aluminum, thick or thin. What varies, what gets decided, what has history and geography and human judgment woven through it, is the vast structure built around those electrons, the choices about voltage and frequency and material, made by people trying to solve practical problems with the tools and understanding available to them at the time. And that, maybe, is a good place to start gathering the threads back together, since we've now followed electricity about as far as it goes. We began, a while ago now, with almost nothing at all, a single stray charge, a packet of electrons, or a deficit of them, sitting on some surface, invisible, weightless in any meaningful sense, and yet capable of pushing or pulling on other charges nearby, without ever touching them. That was the seed of everything else. Static charge on a balloon rubbed against hair, a spark leaping between a doorknob and a fingertip on a dry winter afternoon. From that one simple fact, that charges exert forces on other charges across empty space, an entire universe of behavior unfolded, quietly, the way a single dropped stone unfolds into ripples that eventually reach every edge of a pond. From stationary charge, we move to charge in motion, and that motion is what we call current. Not electrons racing through a wire at blinding speed, as it might be tempting to imagine, but something closer to a long line of people already standing shoulder to shoulder in a crowded corridor, each one shifting just slightly when the person beside them shifts, so that the signal to move travels down the line far faster than any single person actually walks. That's closer to what happens inside a wire when you flip a switch. The electrons were already there, packed together, and the shove that sets them all drifting arrives everywhere in the circuit almost at once, even though each individual electron only creeps along. We talked about voltage as a kind of pressure, a difference in electrical potential between 2 points, the thing that makes charge want to move from one place to another in the first place, the way water wants to flow downhill because of a difference in height. And we talked about resistance as whatever stands in that current's way, the narrowness of a pipe, the friction inside a hose, something that turns organized electrical motion into heat, which is why a wire glows in a toaster and why a phone left charging under a blanket can grow warmer than it should. We followed current through circuits, learning that it needs a complete loop to flow at all, a closed path from source back to source, which is why a single frayed wire, a single loose connection, can leave an entire string of lights dark. We saw how components arranged in different ways, in series, one after another, or in parallel, side by side, change how that current distributes itself, why one blown bulb can darken a whole strand in an old-fashioned string of lights, while in a modern house, one dead bulb in one room leaves every other room untouched. We spent time with magnetism, which turned out, quietly, to be almost the same phenomenon as electricity wearing a different coat. The two so tightly bound together that a moving charge creates a magnetic field, and a changing magnetic field, in turn, can push charges into motion. That relationship, discovered gradually across the 1800s by people like Ørsted noticing a compass needle twitch near a wire, and Faraday spending years testing induction in a workshop lit by candlelight, is the very principle a generator relies on: coils of wire spinning through magnetic fields, or magnets spinning within coils of wire, converting the mechanical motion of falling water or expanding steam or turning turbine blades into the electrical current filling the grid. And that, from there, is where the current heads out into the wider world, up through transformers that raise its voltage for long-distance travel, out across transmission lines, strung between towers marching over hills and fields, down again through further transformers at substations, and again through the small transformer near your street, before finally settling into the calm, steady form your home's wiring was built to receive. It's a long chain when you trace the whole of it, from a single stray charge to a lit room. But every link in that chain follows from the ones before it in a way that, once you've seen it laid out slowly, starts to feel less like magic and more like a very elegant kind of plumbing. Quiet water finding its way downhill, through pipes engineers spent well over a century designing, adjusting and refining, mile by mile, decade by decade. There is something rather comforting, actually, in realizing that the light glowing softly somewhere in your room right now, if there is one, or the quiet hum of some appliance resting nearby, is the end point of a story stretching back through Faraday's careful notebooks, through Ørsted's twitching compass needle, through the very first crude batteries stacked from metal discs and salt water, through the accidental sparks and static shocks that curious people noticed and wondered about long before anyone understood why they happened at all. None of it required you to think about it, of course, for it to work. The current doesn't wait for understanding. It simply flows, the way it always has, obedient to the same handful of underlying rules, discovered slowly, one careful observation at a time. And maybe that's a fitting thought to close on tonight. All that motion, all that history, all those turning generators far away, feeding wires that eventually just settle into stillness right here, into whatever quiet current is humming faintly nearby, powering nothing more urgent right now than the low, steady hum of a room settling into sleep. The charges will keep moving. If there's still a current running somewhere close by, they always do. But you don't have to follow them any further tonight. You've traced the path all the way from a single spark to a spinning turbine and back again. And that's a long way to have traveled, gently, without ever once needing to move. Let the current do what it has always done, quietly, in the background, tirelessly, indifferently, while everything else grows still. Rest well.